Good day everyone, I would like to present our work, Learn to Unlearn for Deep Neural Networks, Minimizing Unlearning Interference with Gradient Projection. Deep learning has widely adopted across various fields. However, machine learning models may unintentionally memorize their training data to a certain level, and recent work has shown that it is possible to derive meaningful information about individual training examples using only the parameters of a trained model. When the training data potentially contains privacy-sensitive user information, this creates significant challenges in regulating access to each user's data or enforcing personal data ownership. Therefore, it becomes imperative to develop machine unlearning techniques that remove such model memorization when necessary, which is the main focus of this paper. Specifically, when users invoke their right to be forgotten, it is crucial to ensure that the user data is unlearned from the trained model. This means that any information derived from the requested to delete data should be removed from the model's knowledge. The unlearning method needs to be much faster than retraining and may need to work without requiring the training data, as the training data may be no longer accessible due to privacy concern. We propose an unlearning method for classification task with a novel unlearning loss function. The method utilizes gradient projection to remove information from a trained model with minimum interfering to important information of the retaining data. The proposed method only requires the forgetting data during the unlearning process and is applicable even when the training data is no longer accessible due to privacy concern. Our work can be applied to depoisoning application to eliminate harmful effects of poison training samples. Our method can be scaled effortlessly to any model and dataset. Our unlearning method can produce models that behave similarly to models retrained from scratch across various metrics. First, I will present the problem statement of machine unlearning. Given the training dataset D and a model F that is trained on D, let DF be a subset of the training dataset, whose information we want to remove from the model F. Named as forgetting dataset, let DR be the complement of DF, whose information we want to retain from the model F. Named as retaining dataset. In machine unlearning, we want to unlearn information of DF from the model F, such that the unlearned model is similar to the model that is trained from scratch with only retaining dataset. The unlearning process should be faster than the retrain process. It would be necessary to develop unlearning method that works without requiring the retaining dataset, since it might not be accessible anymore due to privacy concern. Our approach leverages the property that stochastic gradient descent updates lie in the span of input data points. Inspired by recent works, we have developed a method to selectively forget parts of a dataset by applying gradient updates orthogonal to the core gradient space of model weights computed using the retaining data. This approach allows the model to update its weights in a way that discards information about the forgetting data while preserving the knowledge learned from the retaining data. We first propose the loss function that reverses the learning process as follows. In which the first term is reverse cross-entropy loss, which tries to minimize the predicted probability of the true label class. The second term attempts to maximize the entropy of the model outputs, thereby making equal confidence scores for all classes. The second term also prevents the confidence scores of the forgetting data from going arbitrarily close to zero, which could otherwise result in abnormal confidence scores for the forgetting data. For the depoisoning application, we use lambda smaller than 0 to minimize the entropy of the model outputs. This means that we want the model to assign a high confidence score to a class other than the poisoned labels. We then present how to compute the core gradient space of the retained dataset even when the retaining dataset is no longer accessible. Then we can compute the basis vector and eigenvalues for full dataset input representation by using SVD as follows. Note that the covariance matrix can be computed in mini-batch manner, making the computation very efficiently, even for large dataset. We then store the basis vectors and eigenvalues. From the basis vectors and eigenvalues, it is impossible to reconstruct original dataset. Hence, our method can avoid the privacy concern over storing training data. Whenever a data deletion request is received, we can compute the basis vectors and eigenvalues for the retaining dataset without accessing the retaining dataset as follows. Finally, the core gradient space is obtained by first k vectors of the basis vectors of retaining dataset. Given the forgetting dataset and the loss function, we can compute the gradient. Before applying the gradient step, the gradient are first projected onto the core gradient space, and then projected components are subtracted out from the gradient so that the remaining gradient components lie in the space orthogonal to core gradient space. As a result, the gradient updates will minimally affect the information of the retaining dataset contained in the model. To evaluate the effectiveness of our proposed method on forgetting samples, we conduct experiments on two different datasets, Site FAR10 and Tiny ImageNet, on three different model architectures: Small VGG, which is a variant of VGG model, All CNN, and ResNet 18. To gauge how similar the unlearned model compared with the retrained model and how much information of the forgetting dataset that the unlearned model still retains, we use the following readout functions. First, error on the test set, ideally small. Second, error on the forgetting set. Third, error on the retaining dataset. Fourth, membership inference attack, which tries to determine if a sample is used for the training process or not. This attack can serve as an effective means of evaluating the forgetting capacity of a model. Next, model confidence. We visualize the distribution of model confidence, entropy of the output prediction, on the forget set. And finally, unlearning time, which should be significantly smaller than the retraining time. We conduct experiments on 3 applications: data removal, in which a small portion of training data is removed; class removal is to remove all samples belong some classes; and depoisoning, which tries to eliminate the harmful effects of poisoned samples on trained model. For the data removal application, we remove 500 samples of class 0 of site FAR10 dataset, which is trained using all CNN model. From the table 1, we can see that the errors on retaining dataset, forgetting dataset and testing dataset are closely matched with those errors of the retained model. Additionally, our method takes only a small fraction of retraining time. Figure 2 shows the distributions of model output entropy of the forgetting dataset. The figure shows that the distribution obtained from our method is matched the best to the distribution from retrained model. Finally, the membership inference attack in Figure 2 shows that our method achieves the best ROC curve and the attackers can only obtain close to random performance on membership inference. For the class removal application, we remove the first 5 classes of tiny ImageNet dataset trained using ResNet 18 model. Table 2 and Figure 3 shows that our method achieves similar performance across various readout functions to the retrained models. Figure 3D also shows that our method results in close to random performance on membership inference attack. Finally, for the depoisoning application, we use the unlearning method to remove the harmful effect of poisoned samples and correct the model to achieve the performance as if the model was trained without the poisoned samples. We conduct experiments with different poisoning budgets from 5,000 samples to 25,000 samples. Table 4 shows that our method can help to remove the harmful effect of poisoned samples and significantly improve the classification results on clean test set and clearly outperform recent works. Thank you for listening. Please check out our source code as follows.